There is, in my opinion, no important theoretical difference between natural languages and the artificial languages of logicians. Indeed, I consider it possible to comprehend the syntax and semantics of both kinds of languages within a single natural mathematically precise theory. On this point, I differ from a number of philosophers, but agree, I believe, with Chomsky and his associates. This is the beginning of the famous paper Universal Grammar by Richard Montague, and it contains in short Montague's project to develop a mathematical theory of meaning for languages, artificial and natural alike. It is from this particular characteristic of Montague's theory of meaning that the adjective universal is used in the title of this paper. In fact, universal here is used in order to denote the applicability of such a framework to both artificial and natural languages. The title itself and the fragment of the paper we presented before both clarify Montague's stance on the philosophical question regarding the importance of formal languages. Before Montague, linguistic semantics was mostly studied by translating expressions of natural languages into various other abstract languages. An example is given by the famous theory of semantic markers proposed by Katz and Fodor in 1963. The theory proposed by Katz and Fodor was met with initial enthusiasm. Even Chomsky was positively inclined, still in a rather skeptical way, towards the theory, as we can deduce from his following alleged comment. Well, I don't think anyone understands anything about semantics, but maybe what Fodor and Katz and Postler are doing has some promise. The theory of semantic markers was, however, soon dismissed. The start of the decline of said theory started when the inability of the latter to deal with quantifiers was noticed. From there, many other criticisms were moved to the theory. One of the criticisms was that this theory fundamentally only dealt with translation, whereas to truly study meaning abstractly, we would need to investigate the relationship between particular expressions in a language and their meanings as metalinguistic entities. Montague's aim, as he himself states in his paper, was that of characterizing the notion of a true sentence in both natural and artificial languages, as well as that of entailment. Such an aim could seem to restrict one's attention to just declarative sentences. Montague, however, in his 1973 paper, already provided hints for how to deal with other types of sentences, such as questions or imperatives. Substantial development in this direction has been achieved by academic research in formal semantics since Montague's time, and in fact, a big part of the continuation of Montague's program was done in the direction of extending his model to such types of sentences. Back to the original aim of Montague's UG paper. How did he achieve his goal? Montague employed model theoretic semantics, that is, the definition of a model using constructions from set theory, and interpreting expressions and other elements of language as set theoretic entities in this universe. Montague Grammar is not interested in particular situations, but rather in intrinsic semantical properties of language. One of the key points of Montague's theory is the adherence to the principle of compositionality, stating that the meaning of the whole is a function of the meaning of its parts, and how they're syntactically combined. Let us now delve into the details of the theory. We will start by introducing some of the preliminary notions introduced by Montague in section 1. First, he specifies that he will use Greek letters alpha, beta, psi, and eta to refer to ordinal numbers, that is, to variables coming from the set 0, 1, 2, 3, 4, and so on. Next, the notion of beta-place relation is defined as a set of beta-place sequences. A beta-place sequence is just an ordering of elements of an unempty set A of length beta. For example, by letting A be the Basque Latin alphabet, the sequence GABON is a 5-place sequence. The order in a beta-place sequence matters, so two sequences containing the same elements in a different order will be regarded as different. The notation used by Montague to denote an arbitrary beta-place sequence is the following. A beta-place relation among members of a set A is a set of beta-place sequences of elements of A. This is an example of a 3-place relation among letters of the alphabet. We used the notion of a beta-place relation we just introduced in order to define rigorously the notion of beta-place operation. A beta-place operation, F on A, is a beta plus 1 place relation among the members of A, such that whenever A zeta with zeta less than beta is a beta place sequence, there is exactly one object x in A such that the concatenation of the sequence A zeta with one place sequence x is in F. We will write f of A zeta is equal to x. A function is an example of a one-place operation. If f is a function, we let f of x be equal to f of the one-place sequence given by the one element x. We now define the notion of an algebra. An algebra is a system containing a set of objects, A, and an indexed set of operations on A, the set f of gamma. Montague singles out two special kinds of operations, identity operations and constant operations. The alpha beta place identity operation is defined with the symbol I alpha beta A, and it denotes the operation returning as output the alpha argument of the input. As an example, if we take I23A of the three-place sequence ADE, we will get as an output D. The beta place constant operation, on the other hand, always returns a constant x, no matter the argument. If G is an alpha place operation on a set A, and H zeta is an alpha place sequence of beta place operations on A, then J of H zeta, which we will call the composition relative to A of the operation G with the sequence H of H zeta, is that beta place operation on A such that G of H zeta of A is equal to G H zeta of A with zeta less than alpha for any beta place sequence A of members of A. The basic operations we defined earlier, which are identity and constant operations, with compositions, will form the building blocks of more complex operations. The definitions of these operations and of composition will be needed in order to define the notion of polynomial operations over an algebra. Let AF be an algebra. We call the class of polynomial operations the smallest class of operations K, such that all of the operations f of gamma are in K, all the identity operations are in K, all the constant operations are in K, and all compositions of the operations in K are in K. Just like other mathematical structures, we can define for algebras, in the sense of Montague, some applications that will preserve their operations. Given two algebras A f gamma and B g gamma, we will call an application H, which goes from A to B, a nomomorphism from A into B, if and only if gamma will be equal to delta, that is, there are the same number of operations, and for each gamma, f gamma and g gamma are operations of the same number of places. H is a function with domain A and range included in B, and if for all small gamma in big gamma and beta place sequences A zeta in the domain of the beta place operation f gamma, we have H of f gamma of A zeta is equal to g gamma of H of A zeta. We now have all the mathematical prerequisites to explore the theory of syntax and semantics provided in Montague's paper. The goal will be an establishment of an homomorphism between the syntactic algebra of a language with the semantic metalinguistic algebra of meanings. But to establish such an homomorphism, we will first need to deal with semantically ambiguous sentences. For this reason, we introduce the notion of a disambiguated language. A language will be formalized as a pair DL-R, where the L will represent the disambiguated language and R will be the ambiguating relation. We can think of R as the relation causing the ambiguity in the language by collapsing two elements of the disambiguating language to the same ambiguity class in the actual language. We call any meaningful expression phi of a language syntactically ambiguous if there are at least two expressions phi prime and phi double prime of the disambiguated language such that phi is related to phi prime via the ambiguating relation R and phi double prime is likewise related to phi. Any language containing a syntactically ambiguous sentence is said to be ambiguous. A disambiguated language is comprised of 5 elements. A. Operations f gamma indexed by big gamma, x sub delta indexed by big delta, s, and delta 0. These objects are, in particular, the following things. The tuple A f gamma forms an algebra, and the sets x sub delta are subset of A, and they're called the sets of basic expressions for syntactic categories of the language. The set delta is called the set of category names. A is the smallest set containing as subsets all of the sets x sub delta and closed under all the algebra operations f sub gamma. X sub delta and the range of f gamma are disjoint for all delta in big delta and gamma in big gamma. For all gamma gamma prime and for all a prime, we have that if f sub gamma of a is equal to f sub gamma prime of a prime, then gamma will be equal to gamma prime and a will be equal to a prime. S is a set of sequences of the form f gamma where f gamma is an operation, a beta place relation of delta zeta with zeta less than beta, and epsilon where gamma is in gamma, beta is number of places of the operation f gamma, and delta zeta will be in delta for all zeta less than beta, and epsilon is likewise in delta. Furthermore, we require that delta naught is in delta. The linguistic meanings of the object just introduced are the following. F sub gamma are the structural operations of the disambiguated language. A is the set of all proper expressions. Delta naught is an index of category of declarative sentences, and S is the set of syntactic rules. Given a disambiguated language U, we will say that the latter generates the family C of syntactic categories if and only if C is a family of subsets of A indexed by delta. X sub delta will be a subset of C of delta for all delta in big delta, and whenever F delta zeta with zeta less than beta epsilon is in S, that is the set of syntactic rules, and A zeta is in C delta zeta for all zeta less than beta, then F of A zeta with zeta less than beta will be in C epsilon. Finally, whenever another family satisfies the conditions 1 through 3, then C delta will be a subset of C prime delta for all delta in big delta. We now define some more sets related to the language L, which is given by a disambiguated language U and an ambiguating relation R. We will call the range of the ambiguating relation R the set of proper expressions of L, which we will denote as PE of L. We call the delta syntactic category of L, which we will denote as cat delta L, the set of objects zeta such that zeta prime will be related via R to zeta for some zeta prime in C delta. We call the set of meaningful expressions of L the set MAL, which is given by the union with delta ranging over the set of categories delta of cat delta L. And finally, we call the set of declarative sentences of L the delta naught syntactic category of L, which is cat of delta naught L. We now move on to develop a mathematical formalism for the assignment of a meaning to sentences in a language. An interpretation of a language, which we will denote with this fancy B, given by B and a set of operations G gamma and a function phi, has three components. A set of meanings, B. This set includes meaning associated to any proper expression of the language by phi. B may also contain meanings which are not assigned to any expression at all. A function, phi, which assigns meaning to all the basic expressions of L, that is, to each member of x sub delta for all delta. And finally, a set of semantic operations, G gamma. B together with such operations will be called semantic algebra, and we require that the latter is similar, in the sense given before, to the syntactic algebra of the language we wish to interpret. The meaning assignment F is then the unique homomorphism from the syntactic algebra of the disambiguated language to the semantic algebra of the interpretation, such that phi will be a subset of F. At this point, the only question that remains to be answered is, what really is a meaning? The notion of meaning will be defined in Fregean terms, based upon a type theory. The set of types is the set of indexes on all the sets of possible denotations. We will explain later what is the difference between a meaning and a denotation. We define such a set recursively as follows. We call big T the set of types. We first claim that small e and small t are in T. E is the type of entities and T is the type of truth values. Whenever sigma tau are in T, then the index on the set of functions from things of type sigma to things of type tau is a member of T. We will represent it as left bracket sigma tau right bracket. For each type tau, there exists a type of the sense of type tau, represented by pair S tau, which is the type of functions from possible worlds to expressions of type tau. Let us now define the notations. The notations will depend on the set E and I, where here E is the set of entities and I is the set of possible worlds. The set of possible denotations of type E with respect to I and E is E, where E is the set of possible individuals. The set of possible denotations of type T is the set of truth values, given by the set comprising of true and false. The set of possible denotations of type sigma tau, which, as we recall, it was the type of functions going from elements of type sigma to elements of type tau, is a set of functions from members of d sigma EE to members of d tau EE, which is the denotations of elements of type sigma to the possible denotations of elements of type tau. And finally, the set of possible denotations of type S tau is the type of functions from possible worlds I to members of d tau EE, which is the denotations of elements of type tau. If J is also a set, which we will call the set of contexts, the set M tau EIJ, which we will call the set of possible meanings of type tau based on the set E of entities, I of worlds, and J of contexts, will be the set of functions from I cross product J to the set of denotations d tau EI. Thus, meanings are functions of two arguments, a possible world and a context of use. Given an expression of a language with an interpretation, and given a meaning of said expression, we can thus derive a denotation of the latter by specifying a particular world and a context of use. Senses, on the other hand, are functions of just one argument, that is, the possible world we want to consider. Suppose that L is a language. A type assignment for L is a function sigma from delta into t such that sigma of delta naught is equal to t. That is, a function that assigns types to the various indices of categories, and in particular it assigns the index of declarative sentences, delta naught, to the type of truth values. A Fregean interpretation for L is an interpretation B for L, such that for some non-empty sets E, I, and J, as we defined before, so basically the entities, the possible worlds, and the context, and some type assignment sigma for L, it satisfies the following extra properties. In particular, B will be a subset of the union with types ranging in the set T of the meanings MT, EIJ. We also require that whenever delta is in big delta and zeta in the set of basic expression x sub delta, f of zeta is in m sigma delta EIJ, which is the possible meanings of type sigma delta given the entities E, the worlds I, and the context J. Whenever f gamma, the beta place sequence indexed by zeta of elements delta zeta and epsilon is a syntactic rule, namely it is in S, and beta zeta is in the set of meanings of with respect to E, I, and J of type sigma delta zeta for all zeta less than beta, then J gamma of B zeta with zeta less than beta will be in M sigma epsilon EIJ. We will call the product I times J the set of points of reference of the Fregean interpretation. We will now define a model. A model is a Fregean interpretation together with a point of reference, ij, which will be given by a possible world and a context of use. Thus, while interpretation gives us meanings, models will give us denotations. We can define a denotation assignment for L. A denotation assignment is a function h with domain A such that for all zeta in A, h zeta will be equal to f zeta computed at ij, where here f is the meaning assignment for L determined by B. With these new definitions we introduced, we are now ready to define what it means for a sentence to be true with respect to a model, and what it means for a sentence to entail another. We will say that a sentence phi is a true sentence of L with respect to the model Bij and the analysis phi prime, if and only if phi prime is in C delta naught, and phi prime is related to phi via the ambiguating relation R, and h of phi prime is true. We will say that a sentence phi is a true sentence of L with respect to the model Bij if it is true with respect to said model and to an analysis phi prime. A token in L is a pair zeta p such that zeta is in the proper expression of the language and p is an ordered pair containing a possible world and a context, namely it is a point of reference. Now let K be a class of models of the language L. Now let phi p and psi q be tokens in L. Then we will say that phi p k entails psi q in L if and only if phi and psi are declarative sentences, and for every Fregean interpretation of L, if BP is in K and phi is a true sentence of L with respect to BP, then BQ is in K and psi is a true sentence of L with respect to BQ. With this said, we have covered the first 4 sections of Montague's Universal Grammar paper. In the 5th section, Montague will cover a theory of translation, whereas in the last sections of the paper, he will actually go on and apply the framework provided so far for intentional logic and then for a fragment of English. Nevertheless, for this video, we will stop here. With this said, I hope that you enjoyed the video and it was helpful to you in some form, and I thank you for the attention.